Chapter 2, Analyzing Data, Section 4, Representing Data. The objectives of this lesson is to create graphs to reveal patterns in data and interpret graphs. Some vocabulary to review is independent variable, and some new vocabulary is graph. When you analyze data, you might set up an equation and solve for an unknown. But this is not the only method scientists have for analyzing data. A goal of many experiments is to discover whether a pattern exists in a certain situation. Does raising the temperature change the rate of reaction? Does a change in diet affect the rat's ability to navigate a maze? Using data to create a graph can help to reveal a pattern if one exists. A graph is a visual display of data. Newspapers and magazines often feature circle graphs. A circle graph, like the one shown below, is sometimes called a pie chart because it's divided into wedges like that of a pie. A circle graph is useful for showing parts of a fixed whole. The parts are usually labeled as percents, with the whole representing 100%. The circle graph shown below is based on the percentages of data shown in a given table, table 2.4. So we have all these different chemicals that exist in the stratosphere, and we want to go ahead and look at them based upon what percentage of them actually exist. So we can go ahead and look at these chemicals, and then we could also go ahead and take this graph to kind of give us an idea of a visual without actually really having to analyze the numbers of which ones are greater compared to the others, right? Which slice of the pie, right, takes up the most and which one takes up the least, and what is the proportion of them with respect to each other. A bar graph is often used to show how a quantity varies across categories. Examples of categories include time, location, and temperature. The quantity being measured appears to be the vertical axis. The quantity being measured appears on the vertical axis, or your y-axis, and the independent variable appears on the horizontal axis, or your x-axis. The relative heights of the bars show how the quantity varies. A bar graph can be used to compare population figures for a single country by decade or the populations of multiple countries at the same point in time. In the figure above, the quantity being measured is magnesium, and the category being varied is in food servings. When examining the graph, you can quickly see how the magnesium of the food content varies. Right? So if we were to go ahead and look at magnesium content on the y-axis, how does that change with respect to the different types of food? And again, we can go ahead and just visually look at these and see, based upon the size of the graph, which one has the most, right? And how they also vary based upon the different types of food. In chemistry, line graphs, most graphs that you create or interpret will be line graphs. The point on a line graph represents the intersection of data for two variables. The independent variable is plotted on the x-axis, and the dependent variable is plotted on the y-axis. Remember that the independent variable is the variable that a scientist deliberately changes during an experiment. Whereas if we look at figure 2.16a, and if we look at this, right, we're changing the volume in this case, and we want to go ahead and see how the mass changes, knowing the density, trying to find the density of aluminum. If we look at figure 2.16b, and this is a graph of temperature versus elevation. Because the data points do not fit perfectly, the line cannot pass through all points exactly. The line must be drawn so that about as many points fall above the line as below it, right? And we call this line, when we go ahead and try and fit all the points together, a best fit line. right? We call that the best fit line. And it's a lot easier with density, right, to get a more straight linear line than it is something with temperature, because temperature could fluctuate. But if we go ahead and look at this, right, not all of these points fall on the line. Some of them do. But we try and get most of them on the line as possible. What we can see here is that as we go up in elevation, we're also decreasing in temperature. But that best fit line, again, gives us an idea of a negative trend of our data. If the best fit line for a set of data is straight, there is a linear relationship between the variables, and the variables are said to have a direct relationship. The relationship between the variables can be described by analyzing the steepness or the slope of the line. If the best fit line rises to the right, then the slope of the line is positive. A positive slope indicates that the dependent variable increases as there is an increase of the independent variable. The best fit line sinks to the right, then the slope of the line is negative. A negative slope indicates that as there is an increase in the independent variable, we should see a decrease in the dependent variable. Right? In either case, the slope of the line should be constant. You can use two pairs of data points to calculate the slope of the line. The slope is the rise or the change in y, right? What we use as triangle y, or this is Greek for delta, which means change in, divided by the run, or the change in x, right? Delta y over delta x is your slope here. So just take two data points, and when you take the two data points, find the difference of them, of your y values, and divide that by the difference of your x values. And that should go ahead and give you slope. When the mass of a material is plotted against its volume, the slope of the line represents the material's density, as seen in the example of 2.16a. If we were to go ahead and take 2 points, in this case we had 2 points that when we had a volume of 20 centimeters cubed, right, we had a mass of 54 grams, comparing it to that of when we had a volume of 10 centimeters cubed, we had 27 grams. We can go ahead and use those numbers to go ahead and calculate the density, right? Density is, as for all intensive purposes, mass over volume, grams over centimeter cubed. And when we get our quotient here, it tells us that our density of aluminum would be 2.7 grams per centimeter cubed. Right? That slope of the line told us the density from experimental data. When the best fit line is curved, the relationship between the variables is nonlinear. In chemistry, we'll study a little bit more about nonlinear relationships, which we can call them inverse relationships as well. More on an inverse relationship, if you've ever seen something parabolic, right, we would call that an inverse relationship. Well, we'll talk more about that in chemistry. Interpreting graphs. You should use an organized approach when analyzing graphs. First, note the independent and the dependent variables, and recall that the y-axis depends on the x-axis values. Decide if the relationship between the variables is linear or nonlinear. If the relationship is linear, is the slope positive or negative? When the points on a graph are connected, the data is considered to be continuous. Continuous data allows us to read the value from any point that falls between the recorded data points. This is called interpolation. For example, if we look at 2.16b, when the temperature of an elevation, we can ask ourselves, what is the temperature at an elevation of 350 meters? So here we have, right, our graph. So this would be 300, 400, 500 meters. Because we have some sort of boundary, a higher and lower limit of 500 and 300, we can go ahead and interpret what would the value at 350 be. right? 350 meters. And it looks like it's falling probably somewhere right here. Well, I'll go ahead and say, what is that, right? 17.75. Right? To interpolate this value, first locate the 350 on the x-axis and note that it is somewhere halfway between the 300 and 400 meter mark. Project upward until you hit the plotted line, and then project that horizontal point to the left until you reach the y-axis. The temperature at 350 meters we'd probably say is approximately 17.8 degrees Celsius. You can also extend the line beyond the point in order to go ahead and get an estimated value for the variables. This is called extrapolation. It is important to be very careful in with extrapolation, however, as it can easily lead to errors and results that are that are not accurate. And again, why we say this is because these are not values in which are somewhat measured. We're going to go ahead and estimate beyond any sort of data that has been recorded. Interpreting ozone data. The value of using graphs to visualize data is illustrated in the figure above. Right. If we go ahead and look at ozone measurements, well, I guess these are values that are averaged between these years in the red line, and these values averaged between these years. The graph shows how ozone levels vary from August to April. The independent variable and dependent variables are the month and the total ozone respectively. Each line on the graph represents a different period of time. The red line represents the average ozone levels between 1957 and 1972, during which the ozone levels varied from about 285 Dobson units and 360 Dobson units. The green line, however, shows the level between 1999 and 2000. At no point during the 9-month period were the ozone levels as high as they were as corresponding between the years of 57 and 72. And again, that could be shown by the graph just here, right? That at no point in this graph were the levels between 99 and 2000, right, anywhere close to the values between 57 and 72. And that's, again, just something you can visually see just based upon looking at this graph. Right, the graph makes the ozone hole clearly evident. It is represented by the dip in the green line. Having data from two time periods on the same graph allows scientists to compare recent data with data from the time before the ozone hole existed. Graphs similar to 2.17 helped scientists identify significant trends in ozone levels and verify the depletion in ozone levels over time. Section summary. Circle graphs show part of a whole. Bar graphs show how a factor varies with time, location, and temperature. Independent, your x-axis variables, and dependent y-axis variables can be related in a linear or nonlinear manner. The slope of a straight line is defined as the change in rise and the over the change in run. Because line graph data are considered continuous, you can interpolate between data points or extrapolate between beyond them.